Hello, Michal. Thank you so much for joining me again. Today we have a bug that uses Aurora, and my first question is what Aurora even is and why do we use it?
Hi, Greg. Thanks for having me here again. To answer your question, I actually would like to show you a diagram because I think it will help us a lot. But basically, an Aurora is an EVM. That's how we call it. So it's an Ethereum virtual machine built on top of a near smart contract. So imagine a regular virtual machine, like let's say Linux in your virtualization software that runs on your, let's say, Windows PC. So it's a computer running inside other computer, and you can say that in case of Aurora it works the same in the similar manner. You have an Ethereum-like execution layer, Ethereum-like blockchain running on top of the near. And how it works is like this. Yeah, how it works is like this. That from the near perspective, it's actually Aurora is just another smart contract. But from Aurora's perspective, it's like completely separate chain. It doesn't really know about the underlying infrastructure that is the near protocol. And the way it works is that when a user wants to use Aurora, then they create a regular Ethereum transaction, the one that you use on normal Ethereum, and they send it to the RPC proxy, which wraps this Ethereum into the new transaction and sends this transaction to Aurora smart contract on the new protocol layer, because ultimately every execution in the Aurora engine needs to be initiated from the near side, from the near perspective. And then the protocol unwraps this. Then the smart contract, the Aurora smart contract, unwraps this Ethereum transaction and executes it in the context of Aurora engine.
So if I have some money if I have some ETH and I want to pay it to someone who uses Aurora, can I do it?
Yes, you can, but not natively. Natively, those are two separate chains. However, it is possible, and that's where bridges come from. And here I have the diagram. I hope that will represent this concept. The bridge is exactly like it sounds. It's a connection between two different environments for them to interact. In case of Aurora, this bridge is called Rainbow Bridge, actually. And it's, there's always two sides to it. It needs to be on the near side, let's call it left, and on the Ethereum side, and let's call it right. They have this very similar contracts that are sort of related to each other. So you have the bridges themselves, you have the connectors, which would be quite important later. And you have the connectors for everything, for anything you want. So ERC20 connector, you have a token and you want the token to be transferred, then you have to have a connector for this ERC20 token on the left side and on the right side for them to communicate. If you want to send Ether, like you asked, then you also need to have this Ether connector on the left side and on the right side for them to be able to communicate.
And how does the process look of transferring something from one side to the other?
Yeah, that's a great question, and those where the relayers come from. Well, one side needs to, let's say that I want to send something from the left side to the right side. I need to execute some transaction on the left side, and we'll go into that in a bit. We need to execute this transaction to let the left side know that we want to initialize this transfer. Then we need to wait a little bit because those relayers are sort of a synchronization services between left and right side. They will, after a little bit of time, they will let the other side know about new transaction, new blocks that were produced on this site, so that the other side is aware of them. Then on the when that's done, I will need to get a so-called proof that it's for my transaction, and I don't need to worry how to construct it. The near blockchain, like the near, there's an API on the near side for this to get this transaction. To get this proof for this transaction, and once I have that, I go to the right side the Ethereum, and I use the connector that I want that I'd like to complete my my transfer. Because let's say I wanted to transfer tokens, so I used ERC20 connector on the left side. I need to use the ERC20 connector on the right side. I just provide my my proof, and because relayers shared the information about my transaction before that, the connector can verify that it was actually my transaction is legitimate. It was me, and they can just send the tokens to me.
So do I understand this right? There's no actual way to send money from one blockchain to another, but we sort of destroy those tokens on one side, and then relayers or those synchronizers tell the other blockchain that we've burned tokens on one side and we can now use them on the other side.
Yes, exactly. Sometimes it's not burning, it's just locking them. That depends if the token was breached or it's native. Essentially, if it's native to the given blockchain and you want to send it, then you just lock it. And if you already have it from somewhere else and you want to send it back, then you burn it. But yeah, it's exactly how you said that. That's how it works.
Great. So can we jump into the code now?
Sure, we can. Okay, so here is actually the ETH custodian contract, which is this connector, but for the Ethereum native asset. This one is actually deployed on the Ethereum side, so the right in our diagram that we've seen before. And what's important here is this withdraw function, because this is what was sort of problematic here. What's important is that we need to, when we want to call it, this is, we are now talking about it from the other way around. This is the last step that we would be taking in the whole process. We need to provide it with the proof data, and we parse and consume this proof. This function, which is defined right here, well, it makes sure that the proof is not too old, that it's valid, and that it wasn't used before. All sensible things here, but the most important thing here is this require statement that makes sure that the proof of whatever we provided, that this proof is related to the transaction that was executed by something that's here called near proof producer account, and this is actually the Aurora smart contract. So you need to make sure that whatever you provide here, it was executed by the Aurora smart contract. Once that's done, you decode the result into something called burn result, which among other things contain a field called ETH custodian, and you need to make sure that this field matches the address of this contract that's executing this in Ethereum side, to make sure that this is the connector that is supposed to be completing the transaction. And then if that's done, then you basically just send Ether to yourself.
And where does the burn result come from?
Yes. Well, first let me show you how it looks like in here, because the burn result is actually quite simple structure. It contains the three fields. There's amount, which is just a number of tokens that you would like to send. Recipient, which is the address that the tokens are going to be sent to. And the ETH custodian address that I already mentioned. And there is actually a very similar structure on the Aurora side. Let me show you. Yeah, okay. So this is this structure that's reflected by this burn result. It's called withdraw result in the Aurora side. But as you can see, it contains the same information. You have the amount, you have the recipient ID, and you have the ETH custodian address. Okay, so now let's see where this withdraw result comes from. And there is a function called withdraw ETH from near. And this function is actually returning this withdraw result. Let's see what it does. Well, of course, it checks authorization, if you are the owner or not, if the contract is paused, and then it calls internal withdraw ETH from near, which is an internal transaction. We don't really need to dive too much deep into it, but this I can tell you that this function is basically just reducing your Ether balance in the Aurora. It's burning those tokens, and it's saving the state of the contract, and then it basically returns this withdraw result, saying that this recipient address, which is provided as one of the arguments, because you will be calling this function. So you want to specify who, like to which address those tokens should go to. Then there's amount, so whatever amount that you just burned on the Aurora side, and then the Aurora contract is actually filling this ETH custodian address by itself because well, it knows the connector on the other side, so you don't need to provide it. You can just it will be specified on your own. Now this withdraw ETH from near is not actually callable because this is also an internal function, but what is callable is a function called withdraw here. This is the function that the user will actually be calling to initialize this bridging process on the left side in the Aurora. As you can see right here, it actually is calling this withdraw ETH from near. It gets the result. The result is this withdraw result that we just seen, and then it's converting them into the stream of bytes, and it converts it into the output. So the output of this whole transaction is this this structure, this withdraw result structure, just serialized into bytes.
So to me, it looks secure so far. Where's the bug?
Let's look at the bug now. Yeah, okay, so just as a summary, for now we know that if we want to withdraw the tokens on the Ethereum side, the most important thing that we basically cannot go past is that the executor ID needs to be this near proof producer account. So the transaction had to be executed by the Aurora contract on the right side, sorry, on the left side in the near blockchain. If that's the case, then we'll have our token transfer. And here is sort of a high-level overview of this process. On the top, you can see the legitimate way of doing this. So you burn the ETH on the near side. You wait a little bit so that this transaction is relayed to the Ethereum, and then you when that's done, then the so-called light client. Those have different names, but those basically are those relayers that share this. This information will know about it, then you will be able to receive proof, and with this proof you can complete the whole process in the ETH connector, which is this ETH custodian contract that we looked at before. And now in the bottom there's a vulnerable version of this process, and as you can see, the Ethereum side remains exactly the same, and all that
I struggled to find the difference between these two at first.
Yes, and that's because the only thing that's changed is how you initialize the process. As you can see, normally you need to burn ETH, and you do it by calling this withdraw function, and it turns out that it's possible to make the Aurora produce the same output as though you would burn the Ether, but without actually burning it. You can do it by calling a view function of an eco contract. That will be sort of an exploit for all of this process.
So how does this look? Is this contract even related to this whole flow? It wasn't used normally, was it?
Let me show you actually. I have this contract prepared right here. You should see the eco contract, and I know that it's overwhelmingly short. So
this is the exploit contract.
Yes, this is the exploit contract, and
how much money you could steal with those 13 lines?
Yeah, there was about 50,000 Ether stored in this ETH custodian contract, and every single one of this Ether was susceptible to this vulnerability. That could be stolen. And at that time, with the ETH price in that day, it was about $63 million.
Wow, but it looks complex with these assembly functions. What do they mean?
Yeah, so all this contract does is takes whatever input the user provided and then outputs it almost in exactly the same manner. There are some changes, but they are related to the EVM internals of how this is processed, and it's not actually very important for this to understand this exploit.
Yeah, I guess it's probably a typical thing where For the exploiter, it's quite natural, and then when you read the write-up, it looks like crazy operations, but they're actually not.
Yeah, exactly.
But how would we call this? With what argument?
Sure. So let me show you the Aurora code. So we know that there is this withdraw function, but there is also a view function defined, which is intended to call view function in the Aurora contracts, because Aurora is an EVM. You can deploy any contract there. That's totally legit, and that's the way it's supposed to be actually working. And you may need to want to call those functions. So what you do here to initialize the exploit, you deploy your own contract, which is this eco contract that we just seen, and then you call the view function with a specific arguments. What are the arguments? The arguments, well, as you can, as you remember, the eco contract will basically just return whatever we will send to it. So we need to make it look like it's going to return something that will look like a burn result. And now, if we read through this, now we have these arguments here that are provided by the user, and we are calling a function called view with args, which is defined right here. It's just a wrapper for another function that's called view, and view is actually right here. We get the parameters. We are calling the specific function that we want to call, and then we get some result, which, as you can see here, I hope you can see it well, is a vector of unsigned numbers of 8 bits length, which is basically a byte. So this is just a byte string, and then you convert it into the result and return it like so. Now I hope that you still remember this withdraw it from near function, because it also only returns this structure, which is then in the withdraw function right here converted into bytes, and you return the bytes. So if you have your eco contract deployed in the Aurora, you can just provide a specific string of bytes that will look like that when they will be deserialized into this burn result structure, they will look like something that makes sense. So what you need to provide is some bytes that will represent the number of tokens you want to send, then bytes that will represent the address of the recipient, so probably your own address in Ethereum. And then you will need to also provide address for the ETH custodian, so that when this structure is deserialized, the ETH custodian contract would be able to verify that that it is supposed to be actually executing this transaction. This is the connector we want. But ETH custodian address is public knowledge. You know it, so there is absolutely no problem in you just sending this transaction and receiving it, and receiving the output. And what you need to do then is just wait, because this is the only difference in the whole process. Then you're waiting for the whole for this relayers to let know the other side, in this case the right side, the Ethereum side, about the transaction. Then you need to get the proof, but there's no reason you wouldn't get any. You don't need to worry about it, because this is a legitimate transaction that happened in the Aurora. So you get this proof as any other via the API, and then you send it to the ETH custodian contract, which will deserialize everything, and with it this will result in the successful transaction, and you would be able to withdraw Ether. Not any amount that you want, because there's some limitations to it for the maximum number. But then you can just keep executing this transaction and slowly drain the ETH custodian contract from its
So to sum up and confirm I understand it correctly, we need two things for this transaction to happen. We need the withdraw function, an output from the withdraw function to have a proper structure, and we need this to be a trusted contract address. But the view function allows us to output pretty much whatever we want, so we can use the structure, and it's the same address, so this is also taken care of, and the rest of the transaction is legit. Is that right?
Exactly. Yes, that's exactly how it is.
So amazing bug with so much money to be stolen. Great. It wasn't exploited in the wild, was it?
Oh no, it wasn't. Thankfully, it was reported to the Aurora team, and they could fix it. I can actually show you the fix for it because it's actually quite interesting.
Okay.
The fix was in the 2.6.1. Well, basically, the Aurora team added the return output function, which parses the output of the whatever transaction that happened. It's, for example, the view transaction, and then it checks for the length of this value and what this value is. And if the length is at least 56 bytes long, and those range of bytes is the custodian address that is known, then the chances are that this is an exploit for this vulnerability. So basically the contract just panics and says that it's illegal return. And as far as I can tell, it's still, it looks like just a hotfix for this vulnerability, but it's still there. And this is how it's fixed. I don't think it was, there was something else implemented as of right now, at least.
Okay, that's funny. Thank you so much for joining us and explaining the bugs to us, Michal.
Thank you so much for having me.